So now we want to do some actual computing of limits here. So recall here from Calc 1 that if you take the limit of 1 over x to the r power, r is a fixed power, as x goes to infinity, that equals 0. So numerator's fixed, denominator's getting bigger, ratio goes to 0. So also, if you're just instead of considering real numbers x, all real numbers, you're just considering natural numbers, same thing works. So this is just sum of the points that are on this function. So 1 over natural number to a power also goes to 0. And then all the familiar limit laws apply to sequences, convergent sequences at least, that did for regular functions. So if a sub n and b sub n are convergent sequences and c is a constant, limit of a constant is a constant. Limit of the sum is the sum of the two limits. Limit of the difference is the difference of the two limits. Constants, inside constants factor out here. So limit of a constant times an is constant times limit of an. Limit of the product is the product of the two separate limits. And then limit of the quotient is the quotient of the limits as long as the denominator limit's not equal 0. Can't take a quotient with 0 in it. Also, the sandwich theorem works. So the sandwich theorem for sequences says if you've got an, bn, and cn, bn is trapped in between an and cn, at least past some value of n, then if a sub n approaches a limit L and c sub n approaches a limit L, then this b sub n that's locked in the middle there, sandwiched in the middle, it's also got to approach L. So limit a sub n equals limit b sub n, or I'm sorry, that would be c sub n, the outside. If those two limits equal L, then that implies that the limit of the b sub n's is also L. So it's squeezed in between, it can't get out, it's got to go to the limit L. Also, sometimes it's easier to look at the absolute value sequence, and if an absolute value sequence goes to 0, then the original sequence also has to go to 0. And then L'Hopital's rule also works for sequences. You just have to convert to the corresponding function on real numbers, because remember, L'Hopital's rule needed a continuous function. And then last theorem, if you take the limit of r to the n, as n goes to infinity, you're going to get 0 if r is between -1 and 1. So you take powers on numbers that are less than 1, they get smaller. Equals 1 if r equals 1, and then it diverges for all other values. So if your number is bigger than 1 and you take powers on it, it's not going to converge to anything. Alright, so let's take a look at an example here. We want to find the limit as n goes to infinity, 2n over n minus 1 minus 2/3 to the n. So first thing we'll do is split this guy up to limit n goes to infinity, 2n over n minus 1, and then minus, that's this minus sign, limit 2/3 to the n, again n going to infinity. So in this piece, n is going to infinity, we can divide by the highest power, so it actually is the same thing as looking at dominant terms here. So limit n goes to infinity, highest power is n, so we'll do 2n divided by n over n divided by n minus 1 divided by n. So I multiplied by 1 over n, top and bottom. So these guys cancel, leave a 1. This is, whoops, and then minus limit 2/3 to the n. Well, actually, limit 2/3 to the n, that's this, okay? And it equals 0 if r is between -1 and 1, and this is definitely between -1 and 1. So we actually can put a 0 in there, And that limit's all computed. And now we'll go ahead and finish up on this one. So this is now limit n goes to infinity. And we've got 2 over 1 minus 1 over n. So as n goes to infinity, this piece approaches 0. So that limit is just 2 over 1, or 2. And then notice if we would have looked at the dominant terms here, 2n over n, the n's would cancel, and you'd still get that limit of 2. And that's okay. This is why dominant terms works. Okay, let's look at another example. So here, limit of n squared, log of n squared over 3n minus 1, n's going to infinity. We'll notice here as n gets bigger, log of n squared, and we can actually pull that 2 down in front, properties of logs. That's going to go to infinity, and the bottom's also going to go to infinity. This is form infinity over infinity. So let's go ahead and pull that n down, and then we'll want to do L'Hopital's rule. So this will be n goes to infinity, and then I've got 2 natural log of n, and we're dividing by 3n minus 1. Okay, and then L'Hopital's rule is only for continuous functions, so we have to change this to limit x goes to infinity, 2 natural log x over 3x minus 1. Now that is infinity over infinity, and it's continuous. We can use L'Hopital. So this will be limit x goes to infinity. And let's see, derivative top and bottom separately. So this will be 2 times 1 over x. And on the bottom we've got a 3. And so as x goes to infinity, 1 over x approaches 0. So 2 times 0 over 3, 0. So that limit is 0. Okay, but it's real important that you change to x here, because you can't apply L'Hopital's rule on the natural numbers. Have to have continuity. Continuity of this function has to be defined inside a whole interval. Okay, and then we had already looked at the limit of s sub n, where s sub n was that piecewise function. It was 1 over n if n was odd, and it was n if n was even. And this limit did not exist. Because the 1 over n terms were going to 0, but n, whoops, said 0, wrote infinity. We're going to 0, but the n terms are approaching infinity. They're not approaching the same thing. Okay, if there's a limit, it has to be unique. They have to be approaching the same thing. Okay, and then one last example. So cosine n pi over 4, that thing actually jumps around a bit, but it's always between 1 and negative 1. This is one where we can use the sandwich theorem. So negative 1 is less than or equal to cosine of n pi over 4. Which is less than or equal to 1, because cosine's always between 1 and negative 1. And we want this expression in the middle, so let's divide through by n squared, which is positive, so that preserves all the inequalities. And then this function is sandwiched in between the two outer functions, and as n goes to infinity, this guy approaches 0, and this one approaches 0. So this has to approach 0 by sandwich theorem. So this is 0, and that's a sandwich theorem. Or squeeze theorem, however you want to call it. So I would want to see this work here, you know, if this is a test question. All right, with that, you should be able to attempt section 11.1, problems 6 through 10.